So I'll just go right ahead. I sort of feel like I'm preaching to the converted here. Of course, as data scientists, we spend 80% of our time manipulating data, and that's no secret. So it makes sense to be really good at doing it. So this is my definition of all the data tools that are out there. Up the top, what I call trivial data, data that can fit into Excel. You can easily manipulate using a pivot table, etc. And then small data is what we consider data you can fit into RAM. So that's R and Python territory. And of course, there's big data right down the bottom where you typically need a sort of Spark to handle effectively. And there's this middle part here called medium data that I feel that's not a lot of great tools in R to deal with at the moment. So that's why I developed this disk.frame package for dealing with medium data. So medium data is basically data that can fit onto your hard drive, but that doesn't fit into RAM. I think of the ideal medium data tool as having these three properties. It's got to be free. It cannot be like a SaaS. Got easy to set up and fast. And I think I would say that Spark is actually not that easy to set up. And even if you did set it up, it's sometimes very hard to tune for good performance. I did a little bit of benchmarking, and for one of the use cases, I found that disk.frame is faster than Dask. I haven't done very comprehensive benchmarking yet, but this is where I would see the major medium data tools sit in terms of freeness and speed. So you can see that I'm not a big fan of SAS. Right. Now, how does disk.frame work? It's actually really simple. You just basically, it's a bit like Parquet. So you just have a folder, and inside this folder you store all the big data set as smaller files or smaller chunks. So each of these files here is basically a chunk of the big data set, and I will have a metadata folder to store other things that are, for example, indexed to make it easy to look up the data. And that's as simple as it is. And the file format that I'm going with at the moment is the FST file format. It's basically a very R-centric data format, and it's got really great properties I'll talk about in a bit. So really, these are the key ideas of disk.frame. Break a big data into smaller chunks. And once you've done that, what happens is you can apply all your cores, all your CPU cores, onto each chunk of the data. And you can process your data in parallel. And of course, the FST format that I use has great disk compression. So it compresses your data down to a really small size. And what that means is you can load and write these data sets really quickly. An extension idea is to apply online algorithms to disk frames so that you can, for example, fit logistic regression on these big data sets. And really, I like to thank all the package developers, and I just called out for them. I know tidyverse is not technically one package, it's a lot, so we want to say thank you to the developers of Data Table and Future and FST for making disk.frame possible. All right, so what I want to do now is quickly go and show you what I call a demo. Oh, it's not a demo. This one, yep. I can't really run the demo because the data set is quite big, only sits on my laptop, but what I did do is save it down and really load it into this package, into these RPubs. So the first thing I did, of course, is just I loaded my disk.frame package, and this is really what happens when you load a disk.frame. So what I start with is I just go, this is the file path of where my this disk.frame folder is, and you can see there's a bunch of files in there. And all that you have to do is say disk.frame and then pass it the path, and that becomes a disk.frame that you can use. And when it prints, it tells you how many chunks there are, how many rows, and how many columns are in this disk.frame. And as you can see here, I'm manipulating about 1.8 billion data rows. This is from the Fannie Mae data set. And I've implemented simple functions like n row, n column. You can look at the head, tail of a disk.frame, just like you would any data frame. And what I really want to talk about really quickly is a simple group by example. So in SQL, this is roughly what I'm trying to do. I'm trying to select a column. I want to summarize it by summing up some column. I want to do a count as well. I want to compute the ratio of these two. And this is what you would do in SQL. Now, the thing that makes disk.frame deal with like 1.8 billion rows effectively is that if your analysis only makes use of 1 or 2 columns, just bring those 2 columns into memory. And this is how you do it in disk.frame. You have this function called source keep, and basically says, my analysis only makes use of these 2 columns. Only bring these 2 into memory. And the rest, as you can see, just very standard dplyr syntax. So I've just grouped by this and summarized by this. Now, one thing that I would point out about disk.frame at this stage is disk.frame is a very low-level API. So when you do a group by, what happens is it's doing a group by within each chunk. And to get the correct result that you want, you need to basically summarize the group by result here as well. The other thing you notice is that once I run all of these functionalities, actually returns right away. And that's because it hasn't done any work yet. It just saved what you wanted to do. And then when you call collect, you actually perform the group by operations for each chunk. So it's basically applying this to each of the 500 chunks. So next thing I do is I just call collect. And remember, this data set has 1.8 billion rows. So it sort of finishes within a minute. So it's done the summary within all 500 chunks and brought it into memories. But at this point, it's still not correct. You need to summarize it a second time. And this is where I take the data back in, I summarize it a second time, and then I get the result. And of course, once you collect, the data is in memory. So at that point, you run a group by again, it becomes really quick. So I can summarize 1.8 billion rows in about just under 1 minute. And this is the chart that you can produce from 1.8 billion rows to this chart. This is just a summary of the default rates during the GFC. Not during the GFC, from early 2000 to about 2016, or the American mortgage data set from the Fannie Mae. Okay, so having seen a demo of sorts, I'll go back to my presentation. It would be, PowerPoint, of course. So, so the question is, oh, great, you can use a disk frame, but how do you even go about creating one? So what I've got is a lot of data sets come in CSV form. So what you do, you just call this function called CSV to disk frame, and there's a lot of functionalities implemented. Some of them are fairly straightforward. That's your input file, that's your output file. Shard by is basically the ID variable that you want to distribute your data set by. So for example, shard by would be your account ID or custom ID, something that will distribute your data across the chunks evenly. And sometimes the one CSV file is too big for you to read in. This is where you use in chunk size. You just go, I want to read in 10 million rows at once. So you go in chunk size equals to 10 million. Then it will only read 10 million rows from the CSV at once. So I'm not going to go through too much about the shard key function, but what it does is, say your shard key is account ID, then it computes a hash on that account ID, and then it does a mod over the number of chunks you want. So then roughly, if you've chosen your shard key properly, each of the chunks should have roughly equal number of rows. But if you're not reading from a CSV, you could be using this function called add chunk. So imagine I'm reading from a database system. I can just read in 10 million rows, call add chunk to add the new chunk to my disk frame, and I keep calling this in a for loop, for example. Then I can build up a disk frame that way. Now, using disk frames, once you've libraried it, the first command you should probably run is just set up disk frame, and they will tell you how many parallel CPU workers you want to use in the background. And of course, I've shown here run disk frame on the folder that contains all the FST files. Then the result of that would be a disk frame that you can manipulate, and you can do all your dplyr operations over. Also, disk frame, when I first started making it, I actually sort of try to use data table syntax. So this is a valid data table syntax in disk frame. So you can do a disk frame and do a sum of the variable x grouped by this. And of course, this analysis only requires 2 variables. So I should do keep equals to these 2 variables, and they will make things run really, really fast because you're only loading these 2 variables into memory when you do the analysis. And all of these dplyr functions have been implemented. One thing I would point out is that a range only sorts within each chunk. So it's not like sorted universally. That's fine. Source keep, very important. If you want to only use column 1 and column 2, use source keep at the beginning of your analysis to only keep those functions. So this is roughly how a dplyr function call would look like. So you just source keep x and y, then the rest you can just use normal dplyr until you do call a collect, after which the data will be in memory. Then you can do manipulate it using whatever you're comfortable with. But by default, it returns a data table. But you can use dplyr syntax on that, no problems. And the key workhorse behind the disk frame is really just these two functions. Delay is just a synonym. It does the same thing as map. So what map does is when you call map, it runs the same function on each chunk and returns the result. So this is two ways of calling map. So the first way, you just return pass in a function to your map, and each function accepts a chunk, and each chunk comes into the function as a data table. Then you can manipulate it however you want. You can fit a linear model and then return another data frame, and then when you collect, it does it all together. It also supports the per syntax, so you can just do tilde, and .x becomes the chunk that you're passing in. So almost all functions are implemented with this map, which is just applying the same function to each of your chunks. And these are what I would consider the big three of data manipulation: the group by, merging, and sort. And I would say sorting is the only one I haven't fully implemented yet. So group by and merging both work on disk frame. And as I've shown before, this is really important because disk frame is a low-level library. So when you want to do a group by, you probably want to do a two-stage group by, and this is one example of it. So suppose I want to do a group by and just basically compute the sum of the ends by the ID. The first stage, one way to do it is to redistribute all the A's into one table and B into one table, and then do that. But that's what I call the hard read chunk. That requires you to put the data, rearrange the data on disk, and that's not really not that really great to do. The better way is the two-stage one, is just to summarize it, basically sum up within each chunk, do the summarization, and then combine them together using collect, and then do another summarization. And of course, you can see that this strategy doesn't work for things like median, but it works great for sum or mean. And as I mentioned, the only join missing here is right join, so just use left join. Really, 99% of the code is in R, 1% in C++, really thanks to the R CPP package. The only function that's not fast enough in R is the hashing function, so I had to code it up in C++ to make sure that my hashing can hash over hundreds of millions of records in sub-seconds. And of course, I've done some experiments connecting disk frame to machine learning algorithms. So for example, you can fit a GLM using the big GLM package using disk frame by passing the data chunk at a time to the big LM function. And I put together a vignette and some example code on the internet that I'll post these slides up on Twitter, so you definitely find all the links to all of these. Thank you very much.
Thank you, Zidi. We have time for a few questions.
I have three questions. You talked about hashing for building the chunks. So can you also have the chunks in natural sequence as they arise in, say, time series? That's question number one. Question number two would be, are you using memory mapping for file access? And number three is, do you have benchmarked the read and write efficiency against the FF package?
I probably didn't understand question one very properly, but question two, I believe, was about, actually, question three was whether I've done benchmarks. I've not done benchmarks, but I use the FST package, and FST package has done quite a bit of benchmarks on their website. And FST is quite efficient if you want to load large amounts of data, read and write from the disk. So that's, I sort of forgotten about question two, actually, when I think about it. Sorry, could you repeat question two, please?
That was question two, I think.
Oh, really? Oh.
So you can chunk a natural sequence?
Chunk? What do you mean by chunk a natural sequence?
such that the chunks are in the same sequence as the data arrives.
Oh, yes,
when
yes.
you-
So if
when
you don't
parse it
supply a
first.
shard by, that's how it would chunk by. It would just go, the first 10 million records is in chunk 1, the next 10 million
Okay,
is in
that's
chunk 2, for
possible.
example. Yeah. You can
Memory
match.
mapping was the second one,
Right.
and it's related to the performance topic.
Okay, memory mapping, I don't do that. I think all the read and write services are provided by FST, so I don't believe they do any memory mapping. They just compress the data, and once you compress it, you can't really do memory map. So I think it's faster to do compression and then read and write the compressed format instead of memory mapping.
Okay, do the benchmarking against the FF. I would be very curious.
Maybe we'll bring up the FST page. You can see the benchmarks here.
Thank you. We had one more question over there.
So perhaps you can go back to the slides where you talk about key ideas. I thought it may be interesting to share, if you can, what's the thrust of the improvement. So each idea can, I guess, add something. Maybe you can split it into 15% of the improvement coming from this idea, or what's the split there?
I think it's really, because I think I just went straight to these packages. Now, Future is really, really great because the underlying parallel package if you want to do something parallel, it sort of requires you to pass the variable that you want to use to the sessions, whereas Future sort of detects all the variables in your environment that you're using in your function, and then just makes use of it. So without Future, it would be a lot harder to code disk.frame, for example, that uses variables that are in the environment. So FST, I'll try to bring up their benchmarking. Of course, data table, everybody knows, makes things run really, really fast. FST, basically, if I can type on this, on the front page, they will have a benchmarks, which basically, as you can see, they compared a few methods, reading and writing to disk, and these are the results. And FST actually outperforms a lot of these methods by quite a bit. So, I mean, and the other great thing about FST is it compresses your data. So if I use Feather, my data set likely end up to be really, really big, but FST compresses them down, so I can manipulate much larger amounts of data on my laptop using FST as the backend format.